Hello and welcome, ladies and gentlemen, to the second webinar of our series about the new GOM software version 2016. My name is Dirk Peters from the Software Development Department. Sitting next to me is Jan Franke from the Technical Documentation Department. Jan will show you the new functions live in the software and I will answer your questions in the question and answer sections. If you have any questions, you can ask them in the Q&A section and I will write down the answers for you. The webinar will be recorded as usual. You can therefore watch the webinar again later or share it with your colleagues. We will show you at the end of the webinar where you can get the recordings. Today, we would like to show you news and improvements of the GOM software 2016 in regard to the virtual measuring room. Auto-teaching will be the first topic. There we want to address improvements of the position generation and the path optimization. Afterwards, we will introduce our new approach for measuring car bodies, our so-called Robogrammetry. With the transfer of measurement programs and a look into our free GOM Inspect software, we would like to conclude this webinar. With this, I will hand over to Jan.
Hello everybody. I also welcome you to today's webinar. Let's start with our first topic for today, the auto-teaching improvements. And I would like to talk about 3 different improvements regarding the auto-teaching. Our first improvement is the implementation of a dialog for the creation of measurement positions. Let's take a closer look at the software in the live demonstration. Here is the new dialog, and I will explain it to you in detail. In the pre-selection, you can select which elements the function will use to create the positions. You can use all elements, restrict the selection to the elements seen in the 3D view, or use elements from tags. The menu measurement series lets you choose whether new measurement positions will be inserted in an existing active measurement series or if the software creates a new measurement series. The options under parameters for real measuring data are only usable if you have real measurement data in your project. The dialog can use this data to teach a project again for improved results. If you have reference points in your project, you can choose to use them later on for the real measuring data or not. To speed up a revision of a creation process, you can select the option Only consider not computed elements. The preview field displays the simulated results and the dependency of the elements and the measurements. If I expand an element, you see all the measurements that would capture this element. It also lets you determine the elements used for the creation process. If you want to use the position creation only with specific elements, restrict the elements by selecting the elements in the preview and then choose Selected Elements in the menu Created Measurement Positions for. For example, you can create element-specific measurement series just for surface points. If you don't select any elements, the software always uses all measurement series. For a better overview of measurements that are not fully captured, you can hide the fully captured elements with this button. As you have seen, the creation process for measurement positions is now transparent and gives you the means to modify the process to complete individual tasks. Let's continue with our next topic, auto-teaching improvements, and I will talk a little bit about the path optimization. Finding collision-free paths in narrow spaces like a car body is a tricky task. That's why we improved the optimize path function to find and create valid paths automatically. You no longer need to invest time to deal with that manually. We'll have a look at this in the live demonstration. Here we have a car body and our ATOS ScanMox 8260. We already have 3 surface points within the car body, and I'm going to use these surface points to create measurement positions. The new dialog already comes in handy and lists the 3 surface points in the preview. The software created two measurement positions and a path with collisions. Now we want to eliminate the collisions by using the function optimize path with resorting. This takes some time because of the complex movement of the sensor finding a collision-free path while going into the car body. But in the end, you will save a lot of time letting the software do all the work for you. As you will shortly see, the function will create a collision-free path with a few intermediate positions. There's our result, and as a little bonus, I will execute the measurement series. You can see that the robot starts from its home position and moves along the validated path into the car body. There it measures the surfaces. And after that, it will move back along the collision-free path to its home position. This function is a great new tool that advances auto teaching with the GOM software and saves a lot of time. The next topic is automatic photogrammetry. A completely new function is the automatic creation of photogrammetry positions. With just a few clicks, you can create photogrammetry measurement series and save a huge amount of time. The function is split in two to consider the availability of reference points in the project. If you don't have any reference points in your project, use the function based on cat and fixture to create evenly distributed measurement positions around the measuring object and a fixture in the form of a bell. If you have reference points, use the function based on reference points to create optimized measurement positions. The used reference points can be measured in reality or created virtually. Of course, you can choose the function based on cat and fixture to create evenly distributed measurement positions even when reference points are available. After you've measured and created an actual point cloud based on the cat and fixture, you can then optionally use the function based on reference points to generate an optimized photogrammetry measurement series. I will show you that process in the software. Here we have our trunklet in the ATOS Scanbox 6130, and we don't have any reference points in this project. That means I have to use the function based on cut and fixture. The software starts to calculate positions and checks if enough images overlap and if scale bars are captured. In the other case, it would also check for hidden reference points and if enough reference points are seen by enough images. The creation takes a little bit, but like I said before, this will save you a lot of time and speed up your measuring process immensely. The result, as you can see, is a complete bell-shaped measurement series. That concludes our live demonstration. On to the next topic, which is Robogrammetry. To begin with, I want to talk about our motivation and give you a little background information. As most of you know, the ATOS Scanbox is a plug-in measuring cell for fully automated 3D digitizing and inspection. With our 4 Scanbox series, we're able to measure small to medium-sized parts. But we missed the solution to measure large and heavy parts like a car side or a complete car body. So we expanded our Scanbox family with the ATOS Scanbox Series 7 and 8 and now have the means to measure even larger and heavier parts. Having a new Scanbox led us to re-examine and thinking about our measuring workflows and tools. Until today, to accurately measure large parts, the part needs to be prepared with a lot of coded and uncoded points. This takes a long time because every single marker has to be applied manually. The next step is to teach a photogrammetry series and execute it. The ATOS Plus camera, integrated in the ATOS sensor, will measure all points automatically. After the photogrammetry, all coded points need to be removed before scanning. Then, an ATOS measurement series is required, which can be created automatically with the software. Each scan must at least capture 3 points to guarantee a high transformation stability. At the end, all of the uncoded points have to be removed. This procedure has multiple benefits. It offers very high precision and control of the process, and the results can be repeated easily. But the very long setup and preparation time is a drawback. So we were looking for alternatives. One option we looked at was the transformation of single scans with best fit without using photogrammetry. This would eliminate the need for reference points and pre-measurements. It would also be independent of temperature influences and robot stability. But the repeatability of this option is bad, and it offers no control of the absolute measurement accuracy. You can see that with the top of the car, where the car body has few contours and the scans are not repeatable. In the next couple of slides, I'll explain why. The object in this slide represents a part with an even surface and limited degrees of freedom. Here we have simply taken 2 measurements, and as there's nothing to stabilize the scans, it is not clear how exactly the scans will overlap. They could overlap only a little bit, or they could also overlap further like this, or even like this. So far, that might be acceptable if you only look at the surface. But when there are features on the surface that needs to be measured, suddenly it becomes a whole different story. As long as the scans only overlap a little bit, the feature will still be at the right position. But when the scans overlap too much, the discrepancy between the nominal and actual is too high. Obviously, this option wasn't acceptable for us. Another approach was to use the robot repeatability, again without using photogrammetry. Robot repeatability means that the process is taught once with a master part, and the resulting robot positions can be used again for further measurements. One advantage of that method is that it doesn't need any points for the measurement series, which means a faster performance. But on the other hand, there are a lot of disadvantages. One problem is that the distance of the robot position to the car body depends on the temperature and the mechanical parts of the robot and may vary. That leads to bad repeatability, no control about the absolute measurement accuracy, and in the worst case, the master part needs to be taught again. It sometimes leaves you wondering about the results and whether the part is really bad or if the robot is off. So we continue to look for a better alternative. Our new reference concept is called Robogrammetry. The process is independent of ambient influences like temperature and robot stability. To measure a full car body in white within acceptable tolerance, it is mandatory to have an accurate reference system to stabilize the transformations. Robogrammetry combines the start positions of the robot for the transformation and the absolute accuracy we achieve by using so-called reference cubes, and is our preferred concept. Reference cubes have both coded and uncoded reference point markers. To keep the setup time of the measuring object short, the reference cubes have a magnetic lower side. That way they can be applied easily and be used again. They allow for a better photogrammetry measurement and an easy digitizing. A transformation without using the stability of the reference cubes leads to difficulties on flat surfaces, like you've seen on previous slides. With Robogrammetry and the high transformation stability for all measurements, we achieve a high absolute accuracy, even in the challenging areas. The remaining question is where to place the reference cubes on the car body. For that, we implemented a new function in our software. The new function, Create Reference Point Positions, calculates where to position the reference cubes on the measuring object. The computation is based on the simulated data of the automatically created measurement positions. Based on the reference point positions, you can automatically create a photogrammetry measurement series with the new function we've shown you. Another new software function is the measurement stability check. The check shows two colors, green and red. If it's green, the transformation stability is stable. If it's red, you need to analyze the measurements and place additional reference cubes in the red areas. Now let's go to the live demonstration, where I will show you the workflow. Here you see a complete car body in white within a double robot cell, the ATOS ScanVox 8260, and two measuring setups for each side. To shorten this demonstration, I have prepared all the mandatory steps in advance, and I will walk you through the process in the right sequence of the workflow. First, you have to create or import a measuring plan. Depending on how many features you want to measure, this can take some time. Then you can create measurement positions based on the measuring principles of the nominal elements. To show you where the software created the positions, I will now enable the sensor positions. And here we have a nice cluster of sensor positions. Using the simulated data of the measurements, you can create reference point positions. For that, I have explained that we have a new dialog. And this will only calculate the positions for the reference cubes. Now that we have our reference cubes, we can use the Inspect check to check the transformation stability. You see that the car body mostly shows the green color. That means that the transformation stability is okay. And now that we have virtual reference points, we can create photogrammetry measurement positions with the function I have shown you earlier. Here you see the cluster for the photogrammetry positions. The last step would be to find a nice view. You can use our ISO standard views for that. Zoom in on the object so you can see where the positions for the reference cubes are, and print and report page. And then start to distribute the reference cubes on the car body. This video shows the preparation of a car body with the reference cubes. The cubes can be applied outside of the scan box. Right after the scan box is done, the prepared car body can be loaded and measured. That way you can save time preparing another object while the scan box is active. In conclusion, Robogrammetry is a stable measuring process with high accuracy that produces the required results and is reproducible. It is a combination of software features, the ATOS ScanBox and reference cubes, a new type of reference point. It supports and simplifies the application of reference cubes. It also reduces the required time. And as I said before, it is a stable and independent process with high accuracy and reproducibility. Robogrammetry is the ideal solution for a car body measuring when it comes to saving time and creating better results. Our next topic is transfer of measuring programs. Due to manufacturing tolerances, The composition of every rotation table and other hardware components are slightly different, and because of that, every measuring cell is different. That is the reason why every measuring cell needs to be calibrated. Despite of this, we ensured the possibility to transfer a measuring program from one cell to multiple identical cells. Identical in this context means that the version of the cell and the hardware components must coincide. That way you can use completed measuring programs again in other production sites. This saves a lot of time and improves the process. The huge benefit is that after the transfer of a measuring program, the path stays validated and is ready to use. I mentioned that the measuring cells, including the single hardware components, must be identical. The sensors must also have the same measuring volumes and the same revisions. Here we have a fully measured GOM part with a full measurement series. The path is validated and it has high quality results. Now we want to transfer that measuring program into another cell. Here we have an identical cell without any measuring data, and I'm going to transfer the measuring program into it. You can do that by simply drag and drop it. The software checks for collisions and if the measuring volumes are at least 90% identical. Now we have all components of the measuring program in our project. They are available and the measuring cell is good to go. Let's start with our last topic for today, the VMR Timeline in the free GOM Inspect software. The VMR Timeline was requested by our customers. They wanted to only view the simulated movement of the robot along a path without having to own a VMR license to share information and measuring sequences with everybody in the company. This is now possible in the free GOM Inspect software 2016. Let's see how the timeline works in the live demonstration. As you can see, here in the top left corner and in the name, I have opened the free GOM Inspect software, not any professional version. Down in the left corner, you see that the timeline has an intuitive playback bar that you can use to play and pause the movement and to adjust the simulation speed. You can also jump to specific measurement positions by clicking simply in the timeline on the measurement, and the robot will jump to that measurement position. Now let's look at the animation. While the software animates the path, you can rotate the object and also move in or zoom out to better view the movement of the robot. Now I will decrease the speed. You can still move around. And if that is too slow for you, you can speed up the process. In conclusion, you can now view your VMR projects in the free GOM Inspect, and since it is a free software, you can share it with everybody in your company to transfer information and measuring sequences. We really hope that the VMR Timeline is to the satisfaction of our customers. That concludes my presentation. Thank you, and back to Dirk.
Thank you, Jan. We have almost reached the end of our webinar. There are also additional information we would like to mention here. You can download a beta version of the GOM software 2016 already. The open beta program gives you the opportunity to try out new functions and enhancements without affecting your daily business. Please find more information and the software packages under the following path: support.gom.com, download software, overview, GOM software 2016. The final release is planned in July 2016. As mentioned at the beginning, this webinar was recorded. You will find the video for download in the support area and also on the GOM Metrology YouTube channel. Here you can also find a more detailed video about robogrammetry. In addition, we have produced video tutorials for the new functions, which are also available on YouTube and in the support area for download. You can find a detailed list of new functionalities and features in the direct help. We also implemented the links to the video tutorials for the new functionalities. The next webinar in our series is new GOM Software 2016 3D testing and will take place on June 16th. This was the webinar New GOM Software 2016 Virtual Measuring Room. We will stay online for a while to answer your questions in the Q&A section. Thank you very much for your attention. We hope you enjoyed it. Have a nice day and auf Wiedersehen.